So in this video I want to talk about integrals where the integrand contains a factor of the square root of 1 minus x squared. And the moral of the story that we're going to tell is that if in such an integrand there is a factor of the square root of 1 minus x squared, then the substitution x is equal to sine u may be helpful. So the natural question to ask at this stage is, why is this the case? And the reason why this is the case can be seen by drawing a right angle triangle, which I'm drawing here. And in my right angle triangle, I'm going to say that one of the angles is u, because after all, if x is sine u, u is clearly an angle. So here I'm going to say that this angle here is u, this is a right angle, and what we know is that x is equal to sine u, and that means that the sine of u is the ratio of this side divided by this side, and the simplest way to achieve that is to say that this opposite side is x and the hypotenuse is 1. And then from Pythagoras' theorem it follows that the length of this adjacent side here is 1 minus x squared. So let's just check that that's the case. If I square this, I will get 1 minus x squared without the square root. If I square this, I have x squared. I add the squares of these two sides. I'm going to get 1 minus x squared plus x squared. I'm going to be left with 1, and that is indeed the square of 1. So if I say that x is sine u, and I draw such a right angle triangle, I see that the sine of u is x, and I see also that the cosine of u is the square root of 1 minus x squared. So if my integrand contains such a factor, I'm going to be able to write it in terms of u in a way that's not too complicated. It's just the cosine of u, and I can therefore have a hope of being able to calculate the integral. And this is the basic reason why such a substitution is helpful. Now, you may worry at this stage that this is defined through a right angle triangle, and that means that u is restricted to being between 0 and pi over 2. But if we actually look back at where we've defined u, we said x is sine of u, and that means that we also have that u is the arcsine of x. Now, the way that u is defined through the arcsine in terms of the principal value of the arcsine function means that u is restricted to between minus pi over 2 and pi over 2. So u is between pi over 2 and minus pi over 2 because of its definition in terms of the arcsine function, and this is what we call the principal value of the arcsine function. So for half of this domain, from 0 to pi over 2, we can see the triangle works perfectly, and for the other half, from minus pi over 2 to 0, it will actually work, but I'll leave that to you to check the signs and think about it. So on the next slide, what I want to look at is briefly to recall the change of variable formula, and then to present 3 examples. So this is the key formula of changing variables, or the formula for substitution, and what it says is if we have a function of some variable x, I can change the variable and integrate over a new variable u if I rewrite x in terms of u, and then insert by hand, multiplying the integrand, a factor of dx du. In other words, the old variable differentiated with respect to the new variable. So that's a key formula that we ought to know off by heart. And here we have 3 examples that I would like you to calculate. So I'm going to go through them one after another, but my suggestion would be that you try to do them first and then watch the next bit of the video, the second watch the next bit of the video, and the third watch the next bit of the video. And you can always save time by just seeing quickly in the video whether you've got the answer right or wrong. And of course, another thing you can always do, and you should be doing, is once you've calculated an integral like this, you should differentiate your answer to see that you get the original integrand again. That should give you confidence that what you have done is correct. So let's move on to the next slide and consider this integral here. So the first of these integrals that we're going to calculate is this one. So the integrand is 1 over x squared, and also in the bottom the square root of 1 minus x squared. And seeing this square root makes us think, why not try a substitution? And the substitution is going to be that x is equal to the sine of a new variable called u, and that's the substitution that we're going to try. And we're also going to use our formula that some function of x integrated with respect to x is equal to a function where x is written in terms of a new variable, which I'm calling u. We insert by hand dx du, and then we integrate with respect to our new variable u. So what do we have? Well, we're going to need x is sine u, and we're going to also have this square root factor, so we're going to need to write 1 over x squared times the square root of 1 minus x squared, and this is going to be 1 over, and then the first term, the x squared factor, gives us sine squared u, and the second term is going to give us the square root of 1 minus sine squared, so the square root of cos squared, and because cosine is always positive for all values of u that are defined through the principal value of the sine or the inverse sine function, this means I can use the positive root, so I can just write this square root is the cosine of u. So that's our integrand. And the next term that we're going to need is we're going to have to insert by hand a factor of dx du, so let's work that out as well while we're at it. So dx du is the derivative with respect to u of sine u, and that's just going to be the cosine of u. So now we have all of the ingredients ready. We've written the integrand in terms of our new variable, and we have the extra factor, the dx du, that we're going to need to insert. So this means that we can now say that I1, the integral we want to calculate, is the integral of, now our integrand factor is this, so it's 1 over sine squared u cos u, and then we multiply this by dx du cos u, so we get cos of u, and integrate with respect to our new variable. And looking at this, we immediately see that there is a cancellation. The cos u in the bottom cancels with the cos u in the top. So our integral is the integral of 1 over sine squared u, and another way of writing that is to say that this is the integral of cosec squared u du. So that's our integral in terms of the new variable, and when we look at this we hopefully recognize this as a standard integral. So let's just recall that the integral of cosec squared theta d theta is minus the cotangent of theta, something that you can easily check by differentiation. So we can rewrite now I1, our integral, as minus the cotangent of u, and it's easiest now at this stage to draw the triangle. So let me just draw a triangle. U is our angle, the sine of u is x, so these are the sides of the triangle. The cotangent is 1 over the tangent. Tangent is the opposite over the adjacent, so the tangent of u would be x over the square root of 1 minus x squared, so the cotangent is just the other way around, the square root divided by x. So therefore our integral I1 is minus the square root of 1 minus x squared all divided by x plus an integration constant. And this is a result that you can now check using differentiation. And I would encourage you to do that. So the key steps here were to realize that because of this square root factor, a sign substitution might be useful. This is the formula we use. We rewrite the integrand in terms of our new variable. We work out the additional factor that we insert in this formula, and then once we've got everything ready, we could just put it into the integral, and we were fortunate that in this case this was a very standard integral that is easy to perform. So with that, let's move on to the next exercise. So in our second example, we again have a square root factor, root 1 minus x squared. We look at the integrand and we think that a sign substitution might be useful. So we say, let's try x is equal to sine u as a substitution. And in such a change of variables, what we are doing, we recall, is to say that our integral can be replaced by an integral where we take our integrand but rewrite x, our initial variable, in terms of a new variable, and then we have to multiply by hand by the derivative of our old variable with respect to the new variable, and then we integrate over the new variable. So this is the formula we're going to use. Here's our substitution. So again, let's work out the integrand, and let's work out then this factor dx du, and then we can put them together into here and carry out the integral. So if x is sine u, the square root of 1 minus x squared is going to be cos u. So what we're going to have is that x squared over the square root of 1 minus x squared is going to be sine squared u divided by cos of u, and we are also going to have that dx du is the derivative of sine, which is the cosine of u. So what this tells us is that our integral I2 is going to be the integral of sine squared u over cos u, that's the initial integrand, multiplied by cos of u, that's the factor that we're bringing in, and again we see here a cancellation. The cosine of u on the bottom and the cosine of u on the top cancel, and we are left with the integral of sine squared u with respect to u. So to perform this integral, what we have to recall is a double angle formula, and what we recall is that the cosine of 2u is 1 minus 2 sine squared u, which means that sine squared of u is equal to, so we can take this factor over here, take this factor over here, so we have 1 minus cos 2u. On this side we then have 2 sine squared u, so let's divide by 2, and what we're going to have is overall a half brackets 1 minus cos 2u, close brackets, close big brackets. So I2 is going to be the integral of sine squared u, and now we've written it in a way that's easy to integrate. It's the integral of this. So therefore what we have is that I2 is, now there's an overall factor of a half here multiplying everything, so let's pull it through the integral. So we have a half times the integral of 1 minus cos of 2u integrated with respect to u. Now this is a difference of two integrals, so we can integrate this term and then integrate this term. Both of them are of course multiplied by a half, so I'm going to write this as a half, big brackets. The integral of 1 with respect to u is just u, and then we have minus, and it's the integral of the cosine of 2u, so we can guess that this is going to be the sine of 2u. And now if we just think about differentiating it, we can clarify whether the signs and numbers are correct, and the derivative of the sine of 2u is going to be the cosine of 2u times 2. We don't want the 2 here, so let's divide by a half. So this is the result for the integral of this. So that's our answer, plus, let's say, an integration constant. And now what we want to do is to rewrite all of this in terms of our initial variable x. So if x is sine u, u is going to be the arcsine of x. But what about here? Well, here we're going to have to use a double angle formula, and we can write sine of 2u as 2 times the sine of u times the cos of u. So what we're going to do is we're going to say, let's use sine of 2u is 2 sine u cos u. We are again going to use a triangle. So the angle is u, the sine of u is x, so this side here is 1 square root of 1 minus x squared. So from the triangle we can say what the sine of u is, and that's easy, it's our initial variable, it's just x, sine of u is x, and the cos of u is the square root over 1, so it's just the square root. So it's easy to therefore say what the sine of 2u is, expressed purely in terms of x. So this tells us that our final result is that I2 is a half, big brackets, u is arcsine or sine to the minus 1 of x, and this in no way implies a reciprocal, this is an inverse function, and then we have minus sign, and the half here will cancel with the 2 here, so we're left with sine u times cos u. Sine u is x, cos u is the square root, so we have minus x times the square root of 1 minus x squared, and the square root, close brackets. And that is our final result for I2, and again, as ever, you should check by differentiation. So in this calculation the key steps were, first of all, to see the factor, to recall our key formula, to rewrite the integrand, and to also separately calculate the additional factor that we're going to be inserting, to multiply together and simplify where possible, and then we had to make use of this double angle formula, which is a standard thing we do for even powers of sines or even powers of cosines. And then, having written it like this, we wanted to re-express it in terms of the original variable, and to do that for the sine of 2u we again had to use a double angle formula. So again, I would encourage you to check this by differentiation, but now we're going to go on to the final example. So this final example is somewhat different to the previous two, but I think it's a useful thing to consider. The first thing to notice about it is, after perhaps having seen this square root factor, is to look at the numerator. The numerator is a difference of terms, and whenever you have a sum or difference of terms in the numerator, what that really means is you have a sum or difference of integrals. So I3 is actually the integral of 1 over the square root of 1 minus x squared minus x over the square root of 1 minus x squared, all integrated with respect to x. And once one looks at it like this, it should be clear that these are separate integrals, and it might be possible, and in this case it is, to calculate them in very different ways. So this first integral here is actually a standard integral that I think one ought to know off by heart. So all I'm going to say about it is recall that the integral with respect to x of the square root of 1 minus x squared on the bottom is arcsine of x. And if this is something that you're not immediately confident with, I would encourage you to check it using the methods that we've considered for the first two integrals. This is something that you should be able to reproduce quite easily if you've understood the first two examples. As far as the second integral here is concerned, we can of course do a substitution and it will work and it will give us the correct answer, but it's actually harder than it needs to be. So what I'm trying to say is the fact that you have a square root factor like this doesn't mean that you necessarily have to use the substitution technique that we've been using, because what we actually have here is the derivative of the argument of the square root. So this integral can be done really rather simply. So for the second integral, what we want to do is to recall that if we have the integral of a function of a function, and this is multiplied by the derivative of the function here with respect to the internal variable, and then integrated with respect to the internal variable, this is just equal to f of u integrated with respect to u. So it's exactly the formula that we've been using in the previous few slides, but with the procedure reversed. So what we're going to recognize now is that the integral of x over the square root of 1 minus x squared with respect to x is, now if I want to call u 1 minus x squared, then here I have 1 over the square root of u, and here I have a factor of x, and that's almost du dx, but du dx would be minus 2x. But that's easy, I can always multiply by constants without changing anything significant. So in other words, all I'm doing is I'm multiplying by 1. So I put in here a factor of minus a half integral 1 over the square root of 1 minus x squared, and then I'm going to put in brackets minus 2x integrated with respect to x. So all I've done is to take this and put in some constants in a way that all I've done effectively is multiply by 1. But this factor here is du dx if u is the argument of the square root. So we're going to now let u equal 1 minus x squared, and therefore the integral of x over the square root of 1 minus x squared with respect to x is minus a half, and now it's the integral of 1 over the square root of u with respect to u. So this is u to the minus a half. To integrate that, I add 1 to it, which will give me u to the plus a half, and I then divide by the new power, and dividing by a half is going to give me 2. The 2 and the half up front are going to cancel, so I'm going to be left with this minus sign and a square root of u on the top. So this is equal to minus the square root of u, and the square root of u just means the square root of 1 minus x squared. So, all in all, putting things together, so putting terms together, the integral of 1 minus x over the square root of 1 minus x squared with respect to x is going to be, well, our first term we recognised as arc sine of x. The second term had a minus sign here, multiplied by this integral. This integral has a minus sign as well, so I'll make it plus, and then we have the square root of u, but u is 1 minus x squared, so it's plus the square root of 1 minus x squared. And that is our answer for this integral. And again, what one should do at this stage is check by differentiation. So, the key step here, and really the reason I've added this to this video, is to recognize that sometimes you don't always need to use the more sophisticated substitution technique of changing the variable and saying that x is the sine of u, etc. Of course it works for all of this, and it underlies this standard result. For here, this integral, you can use it, but here it's much easier just to recognize that this is up to numbers the derivative of the argument of the square root. And with that, I will stop this video.